using super heterodyne receivers or double conversion in super heterodyne, that is, you are employing the intermediate frequencies, okay, much higher intermediate frequencies than, let's say, for a standard AM broadcast, AM receivers, which is 455 kilohertz. You go to 10 megahertz. That's the first IF stage, and then you apply another IF stage to convert it down to 455 kilohertz, as we have seen before. For example, over here, you see what happened is that you receive, for an AM receiver, you receive an RF signal. Okay, so this is your RF signal received by an antenna, which is between this range, 550 to 1700 kilohertz. Then the first oscillator, okay, which is tunable, having frequency of RF plus the intermediate frequency. It is shifted up. The spectrum, the RF signal is converted up to 10 megahertz. And then again, from the second oscillator, which is at 10.455 megahertz, you shift this center frequency down to 455 kilohertz. Okay, to save the cost of electronics, you do the signal processing before the detection at low frequencies. Okay, so you don't need these IF band pass filters. Another possible approach that we are going to discuss, you won't need this narrow fractional bandwidth or expensive IF bandpass filters, because the fractional bandwidth is small. At high frequency, you need more sections of bandpass filters, which might be impractical to build. For example, for a 0.01% fractional bandwidth, the crystal or a coupled resonator bandpass filter could be very expensive instead of a LC bandpass filter. So we can avoid these double conversions and the mixers. So what we do is we apply a synchronous type of detection as suggested over here. What we do is we bring the spectrum down to the zero intermediate frequency. So the IF is zero. Okay, the IF, the intermediate frequency is zero. It's not 10 megahertz. It's not 455. It's zero. So the evolution of the super heterodynes, which was always towards higher IF frequencies and requires multiple conversions, multiple IF stages, has taken a new twist with the advent of nearly limitless signal processing capabilities, and that is available from the DSP chips. So what we're going to discuss, and whatever we require a local oscillator which has the same frequency as carrier. Everything can be built down into a single DSP chip. So that's a very nice alternate to avoid double conversion or super heterodyne receivers, standard super heterodyne receivers, as we have talked before. So in the direct conversion receivers, again, in reversion to the heterodyne architectures, these are homodyne. By the way, you can call them as a homodyne. Why? Because what you're going to do is you're going to mix the modulated signal with the same carrier frequency that it was modulated at, and you're going to bring it down to DC. Okay, so these are homodyne. You don't need hetero frequencies, same frequency. So and shift the center frequency of the desired signal omega c all the way down to zero. So what happens is as follows. So let's say this is your mixer. It could be any ring modulator. It could be a DSB. Let's say it could be a double sideband suppressed carrier. Okay. So whatever it is. So what it will do is let's consider a hypothetical baseband signal. So let's say this is my omega scale, okay, frequency scale, and then I have a, let's say, a hypothetical message signal M of omega, okay, which is centered at DC. Okay, this is my DC, and the bandwidth of the signal, let's call this B. Okay, since the message signal is real, so its spectrum is symmetric. It is symmetric. Okay, it is symmetric around DC, and so whatever is true from DC to B is true from 0 to minus B. So the bandwidth is not twice B, it's B. Okay, so the frequencies that are contained from 0 to B are contained from 0 to minus B. It's just symmetric. Anyway, so because MT is real, for any real signal, you know the Fourier transform is real and symmetric. Okay, now if you're going to mix it up with let's say a carrier having frequency of omega c, which is which is a non-zero, very high frequency. But what it does is, when you mix it up with the message signal, it simply shifts the spectrum. So let's say this is my DC. Okay. So what happened over here is that somewhere down the line we have this omega C over here, okay, which is farther from DC. So my message signal shifts at omega C, okay. So message signal shifts at omega C, and the shift will be at minus omega C as well, okay, because you can expand this in terms of exponential 1 by 2 j omega ct plus 1/2 e minus j omega ct, but let's not concern ourselves with the negative frequency. So what we have over here is again this message signal, which is shifted at minus omega c. Okay, so that's modulation, shifting of the spectrum at the carrier frequency omega c. And this frequency, if you can recognize this correctly, this is nothing but omega c plus b, right? Then similarly, this is, what is this? This is minus b plus omega c, right? So a little less than omega c. Anyways, so the overall spectrum is conserved, but the spectrum is shifted at omega c. This is what happens in amplitude modulation in the transform domain. Now what you do is to bring this, to convert this modulated spectrum m omega minus omega c down to zero, down back to zero DC, is that you apply a synchronous detector, synchronous demodulation. So by synchronous I mean you use the local oscillator, which can synthesize exactly the same frequency. Let's call this omega ct again. So what it does is it again modulates the signal. So what happens is at the output, so this is my input, this is my modulated signal, this is my local oscillator signal, that is, so if I can call this omega LO, okay, this is my omega LO, and if this omega LO is perfectly matching omega C, you might need a phase lock loop for that, right? Because if this is exactly the same as the carrier frequency, then the result is that you have at DC, you bring down the message signal from omega C over here back to DC, okay, and then you have the replica at another replica at 2 omega C, not omega C, 2 omega C, okay. So there is a sum and difference of frequencies, okay. This is omega C, then omega C minus omega C is 0, okay, omega C minus omega C is 0, and omega C plus omega C is 2 minus omega C. Well, that can be low pass filtered out. So if you're applying a low pass filter, well, this is your exactly m of omega, okay. So this is your m of omega. So what you need is a low pass filter, and for a synchronous detection, you need a local oscillator which synthesizes the same frequency as carrier to actually to detect your original message signal, which is okay. So this has a bandwidth of b, and minus b. Okay. Now, generally, as described before, this requires the signal to be mixed separately with the local oscillator signals of the same frequency, omega C, omega C. You see the difference is that here we are using a 90-degree phase offset in order to produce IQ modulation, okay. You will see what IQ means. That means in phase and quadrature. To preserve all the signal information, okay. So to see this, note that the input signal, which could be a sinusoid, which could be any general piece of spectrum, will in general be out of phase at times with cosine omega ct, and at the other times with sine omega ct. So the outputs of the cosine mixer, sine mixer, they can go to 0, but together these I and Q in phase and quadrature signals contain the information. So what happens is over here we have the local oscillator, okay, that produces the frequency omega C, okay, whatever, or omega C or omega RF, let's call this omega RF, right, and you are receiving omega RF over here, right. You might have a RF amplifier over here, so this could be an RF amplifier, right, and then your after amplification of the signal, RF signal, you're splitting this up down to the first mixer and to the second mixer. The second mixer is 90 degrees delayed, so this is sine omega RFT, and then this is cosine omega RFT, right? And so what happens is, again, you have the sum and difference, right? Just like over here, okay? So there will be this omega c is going to be shifted to 0, and then this omega c is going to shift to 2 omega c, and then for both of these in phase and quadratures, which are 90 degree offsets, you require low pass filters. You require low pass filters to produce the in phase I signal and the Q signal, which in time domain have a 90 degree offsets, right? So how you get rid of this image phenomena is that if you recall that in the super heterodyne receiver, which we discussed before over here, the image frequency was, if you recall, that we set the local oscillator to be equal to whatever omega RF is plus some intermediate frequency, right? Plus some intermediate frequency. And if you recall that the image frequency, now if you are going to mix it up with RF and you are considering the low frequency, then it's omega IF, okay? But now omega IF is 0 over here, you see, because we are mixing up it with the same omega LO is again omega RF. So if this is 0, then this is twice omega RF, okay? So previously the image frequency omega I was equal to was the high frequency. It was omega RF, okay, plus twice of omega IF. Now we don't have this problem over here. Why? Because this image frequency is different from the RF frequency, okay? It's only the difference of the same RF that is going to bring the spectrum down to 0, okay? So omega I multiplied by omega LO, because omega LO is omega C or omega RF, right? It's the same frequency. So the difference has to be 0. For the difference to be 0, these two frequencies, so this frequency and this frequency at the detector site has to be equal. So the difference is 0. If image frequency is different, of course image frequency is different from the received original RF, then it won't produce a spectrum at the DC, okay? It won't produce a spectrum at the baseband. So if it's not going to produce a spectrum at the baseband, then it would be low pass filtered out, okay? It would be low pass filtered out. So for example, here we are considering the local oscillator signals, omega C and sine omega C. Of course, they are 90 degree phase shifted, so they are going to produce IQ, 2 IQ channels. But you don't have the image problem in this setup, okay? So this is yet another nice way to eliminate the image frequency. So to see this, you note that the original signal could be easily reconstructed from the I and Q signals. That is low pass, that is by low pass filtering of IQ signals, that is going to bring back the modulated signal back to the baseband, okay? So you can extract the baseband signal from both IQ channels, IQ signals, and determines the, so you can have a passband receiver, for example, you can have a 5 kHz rectangular pulse, rectangular low pass filter on the IQ signals that would give the receiver a flat passband extending 5 kHz above and 5 kHz below the local oscillator frequency. Okay, so both of the I and Q channels are using low pass filters, right, to extract the baseband signal. So if this frequency, the local oscillator frequency, matches this frequency, whatever this is at modulated, I've written this RF, including at this, actually this is, the antenna is receiving the spectrum at omega C, okay? So this is centered at omega C. So this is my modulated signal at omega C, and my oscillator is also at omega C. So the difference over here is the baseband signal, okay? So it is going to be at 0. So this is my in phase, and then my quadrature, this is again 0, right? And then this can be low pass filtered out. We are not bothered about what happens at actually 2 omega C. So this can be low pass filtered out. We won't get this at the output of the low pass filter. So the classic image problem, uh, which was sphere at low IF frequencies, disappears when IF frequency is 0. Okay, so when you are making the IF equal to 0, you don't have this image problem. So the low frequency I and Q signals can be digitized directly or subsequent digital processing and demodulation. So you don't need any bulky IF bandpass filters, right? At this time, you don't need IF bandpass filters, low fractional bandwidth, and you see even tiny surface acoustic wave bandpass filters are huge there compared to the size of the DSP chips. So with this architecture, nearly 100% of the receiver can be incorporated on a single chip, including a tunable frequency synthesizer, including this local oscillator to produce the local oscillator signals. Okay, so you can have this entire setup on a DSP chip. Okay, it's going to be a very fine, small DSP chip. So this is your direct conversion receiver, and this eliminates the problem of the image frequencies as well. So this is yet another approach that solves the problem of a standard super heterodyne receiver that suffer from the image frequency problem. So this block diagram of a direct conversion receiver, which is shown below. So everything on this diagram plus the local oscillator synthesizer over here is available on a single chip that is intended for use in high definition television receivers, for example. You don't have this problem of image frequencies. Okay, so it's again a method of method of synchronous detection where you are implying the same carrier frequency which was used to modulate the message signal. Okay, so the message signal was shifted at omega c. The difference is 0, so you have the baseband at 0. You don't have nothing at there's nothing at omega c after the low pass filter. Okay. Now there's a very interesting article shared at National Instruments webpage, and those of you who are interested in reading more about IQ modulation, well, it's not very. I mean, to figure out the hardware required for example, over here you had these IQ signals. So, how you modulate and demodulate these IQ signals? It's simple. You see, to understand how to avoid manipulating the phase of the RF carrier directly, what you do is actually you change the phase or the amplitude of the I and in phase and quadrature signals independently, and that changes the phase or amplitude of the modulating carrier of the signal, modulating carrier signal. Okay, so let's refer to the following IQ modulation equations. So if you look here, the first identity, that is cosine alpha plus beta. If you expand this, you have cosine alpha beta minus sine alpha beta, and if you replace this alpha by 2 pi fct and beta is pi over here. Okay, for example, this is your modulating carrier and having a frequency omega c. This can be expanded as such by this trigonometric entity. So this and this is the same thing. Okay, if you're going to replace alpha is 2 pi fct, beta is phi. So you see this is what you get. Okay, once you expand this. Now this cosine has a phase of phi. Okay, which can be seen over here. This is the phase of phi, and it has an amplitude a over here. And basically this is nothing but you see this is I square plus Q square. That's the same relationship under root, right? So similarly, this phase, as you can see from here, tangent of that phase is Q or I, right? That's Q or I. So the idea is that independently, if you change the amplitude or phase of Q and I in phase and quadrature signals, you can change the phase or the amplitude of the modulating carrier. You don't need to change it directly, as you've seen in the phase modulation schemes or amplitude modulation schemes. Okay, so what I mean is, if you can change A over here in I and Q, then indirectly you can change A over here as well. Okay, you can modulate the amplitude of the carrier. So for example, from here to here, the third equation, it's not hard to see that if you're going to substitute this I and Q for A cosine phi is substituted by I over here, and Q is substituted by A sine phi. Okay, so you can write the modulating carrier as such. Okay, so I is the amplitude of the in-phase carrier, Q is the amplitude of the quadrature phase carrier. Okay, why this is quadrature is because you see the sine and cosine have 90-degree phase shift. So actually what you are doing is you have the in-phase signal multiplied by the carrier, and then there's a quadrature signal, okay, that is multiplied by the same carrier which has been phase shifted by 90 degrees, right? So essentially what this fact means is that you can control the amplitude, frequency, and phase of the modulating carrier sine wave. This is the modulating carrier sine wave, okay, by simply manipulating the amplitudes of separate I and Q input signals. Okay, so with this method, you don't need to directly vary the phase of the RF carrier. For example, I don't need to make this phase a function of proportional to the message signals, whatever it is. For example, if it is let's call this MT. Okay, I don't need to vary this directly. I can do this indirectly if I make this phase variation over here and here. Okay, and if you're going to expand this this cosine, then you have this phase modulated by the message signal. So this phase is actually proportional to the message signal. Okay, so you can vary the phase, amplitude, or frequency indirectly through varying those parameters in I and Q signals. So you can achieve the same effect by manipulating the amplitude of I and Q, for let's say for amplitude modulation. So of course the second half of the equation is a sine wave. Okay, so you have a sine wave over here, and the first half is a cosine wave. So you must include in your device and hardware circuit to induce a 90-degree phase shift between the carrier signals used for I and Q mixers. Okay, so just like over here you have a 90-degree delay, right, to produce the I and Q channels. So you have a 90-degree phase delay, but again over here you have you were demodulating this because the local oscillator has a frequency of omega c. You bring it down to 0. So in the frequency domain, that's how it is. You're going to translate it down to DC, and then you are going to low pass filter it. So you need to, in order to produce in-phase and quadrature, you need to have a 90-degree phase shifter in your hardware. That's what it says. So this is a hardware diagram of a IQ modulator. The IQ modulator, what it does is it mixes the I waveform with the RF carrier sine wave, and it mixes the Q signal, the quadrature component, with the same RF carrier sine wave at 90-degree phase offset. So this is 90-degree phase offset. That mixes up with the Q signal. Okay. So I signal mixes with the in-phase carrier, Q mixes with the carrier, which is offset by 90 degrees, and the Q signal is subtracted from the I signal, producing the final RF modulated waveform, just like over here. So you're subtracting this from the in-phase part to produce the modulated RF carrier. So this is modulated. Okay. For example, this phase could have been modulated by the message signal. So it's a phase modulated signal. Okay, which has been produced by the IQ modulator. Okay, so you have separately modulated I and Q to produce a RF signal that is modulated carrier. Okay. In fact, the 90-degree phase shift of the carrier is the source of names for I and Q data. I refers to the in phase because the carrier is in phase, and Q refers to the quadrature data because the carrier is offset by 90 degrees. So this technique is known as quadrature up conversion, and you can use the same IQ modulator for any modulation scheme, for any phase modulation scheme, amplitude modulation, for frequency modulation. And how you do this is you can achieve this by manipulating the amplitude, phase, or frequency of I and Q signals. Okay, so you can indirectly encode the information in frequency, phase, or amplitudes by varying the I and Q parameters independently. Okay, now in most of the receivers, in AM receivers or FM receivers as well, television receivers, you have this automatic gain control. What this automatic gain control is, and what it does is, for example, over here you see we have signal conditioning and time constant. This is your AGC. Okay, it's a feedback loop. You have automatic gain control over here, and for example, this is a standard super heterodyne receiver. From the antenna, you receive RF signal, modulated RF signal. There's an RF amplifier and tuning. Okay, so it could be whatever the channel you want to listen to. Then it goes into a mixer. Okay, and in a mixer you have that mixed up with a local oscillator to produce the signal at the IF stage, and whatever amplification is required at the IF. Then it goes to the detector, and finally you have the audio amplifier, which could be a class B or class AB amplifier to drive the output. So what this AGC does is, over here in the super heterodyne receiver, is that it takes the it's a feedback loop. Okay, so for example, it's taking the information from the output of the audio, and for example, it is taking some maybe bias current from the demodulator. Okay, so these are its inputs, and it's taking some data from the IF as well to detect what the signal level is. If the signal level is high, it's a very strong signal, and you are listening to a very loud sound, it's going to reconfigure the gain of the IF RF amplifier, which is required to produce let's say sufficient milliwatts before the demodulation, so it reduces the gain for a strong signal. Vice versa, if it's a weak signal, it adjusts the gain so that the gain increases and you can still hear the sound. Similarly, it can also change the gain of the IF stage band pass filter if the more gain is required. So actually this AGC is a closed loop feedback regulating circuit in radio receivers, the purpose of which is to maintain a suitable signal amplitude at its audio output. Okay, so this is its audio output over here. Despite the variation in the signal amplitude, so signal amplitude that you are going to receive is going to be from weak RF to strong RF. So accordingly, automatic gain control is going to set the gain of IF stage and the RF stage. Okay, so it's depending on the feedback of the detector, demodulator, the audio amplifier. If the bias current is large, that means the signal is strong, so it's going to reduce the gain. So the average or the peak output signal level is used to dynamically adjust the gain of the amplifier, enabling the circuit to work satisfactorily with a great range of input signal levels. So it is used in most radio receivers to equalize the average volume, loudness of different radio stations, due to difference in signal strength, received signal strength, as well as the variation in signal stations radio signal due to fading. Okay, so if it's a weak signal due to fading, channel fading, it can increase the gain. Without AGC, the sound emitted from the AM receiver would vary to an extreme extent from weak to strong signal, and that could be a discomfort. So the AGC effectively reduces the volume of the signal strong if it is strong and raises it when it is weaker. So it's the same thing. So in a typical receiver, AGC feedback control signal is usually taken from the detector stage over here. There's a detector stage, demodulator stage, and applied to the gain of IF and RF amplifier stages. The other, so besides adjusting the gain, it also helps in avoiding the conditions where this IF amplifiers and RF amplifiers they might overdrive, or they might overload the next stage. Okay, so the automatic gain control can also avoid these situations. Okay, so if for example, if this stage is going to produce a very large output over here, and that means in the next amplification stages, okay, for example, if it's a digital filter, there's a digital filter. It can be saturated. Okay, there could be finite word length effects, for example, and due to the saturation, you will suffer non-linearities, or you will hear the clipping of the sound, for example, if it saturates the next stage. So nearly every receiver has some kind of AGC that is used to adjust the gain of RF and IF amplifiers according to the strength of the input signal. That's one. This is the first point of ADC. The second is that without this feature, that I've said, without this feature, the receiver will overload. So overdriven amplifiers, they go non-linear, or they clip and the output will be distorted. So it's two loads. So one is that they adjust the gain of RF and IF amplifiers according to the strength, and the other is they avoid this condition of overloading of the next stage. So overdriven amplifiers, they can go non-linear, they can clip, and then you will hear the distorted or two load sound. So the output sound level, even for an FM receiver, depending on the design of demodulator, may not vary with the signal level. Because why? Because in FM you are encoding the information in the frequency of the signal. So there might not be variation with the signal level, but overloading of the IF amplifier stages will still produce distortion. So whatever signal processing you're doing at the low frequency, because in if you recall in a FM demodulator, if you're using a band pass filter, that might convert that actually converts the FM to an AM signal for detection. So still you can have this gain problem over there, and overdriven and overloading problem at IF stage. So this might produce distortion. So even FM receivers also need automatic gain control. Okay. So if you say that in FM there is no problem, there is no signal variation, there is no amplitude variation. But at intermediate frequency stage where FM is converted to AM, okay, if you recall, we used the band pass filter before to convert this FM to the slope of the band pass filter actually converts the FM into an AM. So according to the frequency, the amplitude varies. Now, if that happens, that might overdrive or overload the IF stage, okay, and that might produce non-linearity or distortion or loud sound. So you need an AGC for FM demodulator as well. Similarly, television receivers, they also need accurate AGC to maintain for example, the correct contrast level. Analog television or threshold levels, digital televisions, any AGC circuits is a feedback control system. So in simple AM receivers, the diode detector, it provides a convenient DC output voltage that it controls the bias current and hence the gain of the RF amplifier. The controlled bias current can also be used to drive a signal strength indicator. Okay, so for example, over here, the demodulator is providing you the voltage, so that is so the signal conditioning can be done on the inputs, or it can be used to adjust the gain accordingly of the IF and RF stages. Okay, so whatever the output voltage or the bias current you're going to get out of the detector is how the AGC is going to based on that information, AGC is going to control the gains of IF and RF stages, okay, and going to prevent it from being overdriven. The other circuitry of interest in the receivers is noise blankers. Many receivers, including most television receivers, have noise blankers circuits to reduce the effect of impulse noise, such as spiky noise produced by automobile ignition system. So, if you recall, a spiky noise, which is an impulse, a short duration impulse, delta omega, okay, which has an inverse Fourier transform of, let's say, 1. It's a constant. Let's say whatever this constant is, it's a constant. Okay, it's 1 for all t. That means that it's going to corrupt the for example, at the IF stage, it's going to corrupt the entire signal processing for all the duration, and it's not desirable. Okay, so it could be due to automobile ignition. It could be spike could occur due to the weather condition, the lightning conditions. So we don't need this impulse in electronics. Okay, it's going to affect the signal processing severely. So the interfering pulses are of sort of short duration that the IF stage can be gated off briefly while the interference present. Okay, so if you recall this impulse, whether if it's in frequency domain, it's 1. If it is delta t over here, right, if it's delta t, it's spike, then again it's 1 for all omega. Okay, so it's going to correct the entire spectrum. Okay, so they are Fourier duals. This is Fourier dual, because the peak is going to be very short duration pulse. Typically, this is a network. So noise blankers are in IF stage. They are in intermediate frequency section of the receiver. So when a pulse of noise passes through the IF amplifier, it is usually of greater amplitude than the desired signal. Okay, so it has a very strong amplitude. So what it does is the noise blanker circuit momentarily reduces the gain of the IF stage during the impulse, and well, the more complex noise blankers they can use the secondary IF stage as well to have an adjustable threshold and timing characteristics so as to reduce the noise passed through to the audio stages of the receiver. Okay, we don't need this pulse to corrupt the sound that we are listening to at the audio stage. So these noise blankers are employed in the IF stages of the super heterodyne receivers to to actually counter or mitigate the effect of the impulse due to the ignition systems and the lighting conditions. And this noise blanket is best applied before any narrowband filtering is done. Okay, because you narrow down the band, narrowing down the band actually elongates the pulse. So we don't want that. So before any narrowband filtering, the noise blanket has to be applied in the signal path, so as not to introduce the ringing or distortion in the filtered signal. So noise blankers are most useful with AM modulation and single sideband signals. Okay.